Conditional and absolute convergence. Let the series, the summation of an, be a series of real number. If the summation of an converges, then the absolute value of the summation of an converges also. We say that the series converge absolutely. The summation of an converges, and the absolute value of an diverges. We say that the series converges conditionally. For a series to converges absolutely, the first thing, that series must converge. So if the series converge and the absolute value of that series also converges, then that series converges absolutely. But if a series converges and the absolute value of that series diverges, then that series converges conditionally. Now let's take some example. Example 1. Show that the series below converges absolutely. The series, the summation of an, which is equals to summation from n is equals to 1 to infinity of minus 1 raised to the power of n into n plus 1 over 2, all divided by 3 raised to the power n. So we're going to show that this given series converges absolutely. And from the definition above, we have that for this series to converge absolutely, then the series itself has to converge. And the absolute value of the series also has to converge. So when the series converges and its absolute value also converges, then the series is said to converge absolutely. So now let's work with the given series first, which is the summation of an. Now, does the summation of am converges absolutely? Remember that the summation of am is actually equals to the summation from n equals to 1 to infinity of minus 1 all raised to the power n bracket m plus 1 divided by 2 or divided by 3 raised to the power n. Now, does this series converges absolutely? But wait a minute. What type of series is this? If you take a careful study of this series, you observe that this is an alternative series because of this minus 1 here that is raised to the power of n. It means that its sign will alternate. If the first sign is positive, the next might be negative, the other will be positive, and so on and so forth. So this is an alternative series. And to test whether this series is convergent or divergent, we need to use the alternative series test. Now, the alternative series is of this form: the summation of minus 1 all raised to the power n of an. And this series converges if two conditions are satisfied. The first condition is the series must be decreasing, that is, an must be greater than an plus 1. And the other condition is that the limit of an as n tends to infinity must be equals to 0. So when these two conditions are satisfied, then this given alternative series is said to converge. So now let's see if this very one satisfies both conditions. Remember that the series from n equals to 1 to infinity of minus 1 all raised to the power n into n plus 1 divided by 2 all over 3 raised to the power n is a given series. We are going to test by alternative series test if this series converges. Now the alternative series has the form the summation of minus 1 raised to the power n of an. So from this, what exactly is an? Now if you observe, we can simplify this expression to the summation from n equals to 1 to infinity of minus 1 all raised to the power of n into n plus 1 all over 2 times 1 over 3 raised to the power n. Now these two expressions are the same. Now when we compare this expression here with this one, the summation of minus 1 raised to the power n, we have something similar here. So an will be equals to 1 over 3n. So when we compare these two expressions, we have that an is equals to 1 over 3n. So hence an, which is the sequence, is equals to 1 over 3 raised to power n. Now the first condition we need to test is if this sequence is decreasing. That is, if an is greater than an plus 1. Now consider an that is equals to 1 over 3n. Now at n equals to 1, we have that 1 over 3 raised to power 1. At n equals to 2 is equals to 1 over 3 raised to power 2. At n equals to 3 is equals to 1 over 3 raised to power 3. At n equals to 4 is equals to 1 over 3 raised to power 4. And it keep on going in that sequence. Now, 1 over 3 raised to power 1 is 1 over 3. And this is 1 over 9. This will give us 1 over 27. And this will give us 1 over 81. That 1 over 3 is greater than 1 over 9, which is also greater than 1 over 27, and this is greater than 1 over 81, and greater than the next term, obviously. So from this, we can conclude that an is greater than the next term, which is an plus 1. Because the first term is bigger than the second term is bigger than the third term is bigger than the fourth term. So it means that an is always bigger than the next term. Hence, the sequence is decreasing. Thus, the first condition is satisfied. Now, the second condition for this series to converge by alternative series test is that the limit as n tends to infinity of an is equals to 0. Now remember that an is equals to 1 over 3 raised to power n. Now let's find the limit as n tends to infinity of an. This will be equals to the limit as n tends to infinity of 1 over 3 raised to power n. So this is equals to 1 over 3 raised to power infinity. We'll substitute infinity for n, and this is equals to 1 over, of course, 3 raised to power infinity is infinity. And when dealing with limits, 1 over infinity is 0. So hence, the limit as n tends to infinity of an is equals to 0. Thus, the second condition is satisfied. Since an is strictly greater than an plus 1, and the limit as n tends to infinity of an is equals to 0, then the sequence converges by alternative series test. So we have proved that the sequence, which is summation of an, converges. The sequence converges by alternative series test because these two conditions are satisfied. Now, the second condition for that series to converge absolutely is that the absolute value of the summation of an will also converge. Recall that the summation of an converges by alternative series test. Now we're going to check now if its absolute value will also converge. Now the absolute value of the series is equals to the absolute value of the summation from n equals to 1 to infinity of minus 1 raised to power n bracket n plus 1 all over 2 all over 3 raised to power n. Now we're going to check if this series will converge. But how can we proceed from here? Well, with the help of this absolute value, it makes it so easy to simplify. Now, consider this. Consider the absolute value of minus 1 all raised to power n to n. If we were to write out this sequence, when n is 1, it is the absolute value of minus 2. If n is 1, minus 1 raised to power 1 is minus 1 times 2 times 1 is 2. Now when n is 2, minus 1 raised to power 2 is plus 1. Now plus 1 times 2 times 2, 2 times 2 is 4, so we have positive 4. Now when n is 3, if you substitute 3 for n, we have minus 6. When n is 4, we have plus 8. When n is 5, we have minus 10. And it keeps on going in this manner. Now, the absolute value of minus 2 is 2. Absolute value of 4 is 4. Absolute value of minus 6 is 6. Absolute value of 8 is 8. Absolute value of minus 10 is 10. Now, what's the conclusion? That with the help of the absolute value, the negative sign disappears. It's 2468. And this implies that this sequence here is the same thing as 2n, because 2n will give us this when n is 1, 2, n is 2, 4, n is 3, 6, n is 4, 8, n is 5 is 10. And from this we can just deduce that if we have an expression like this, we can simply say that the absolute value cancel the alternative sign. So this absolute value cancel this sign and we're left with 2n. It's as simple as that. Now we can use this logic in this given problem. Consider this. The absolute value of the summation from n equals to 1 to infinity of minus 1 raised to power n into n plus 1 all over 2 all divided by 3 raised to power n, which is equal to the summation from n equals to 1 to infinity of minus 1 raised to power n bracket n plus 1 divided by 2 times 1 over 3 raised to power n. So these two expressions, they are equal. Now, using what we'll deduce from here, that this absolute sign cancel this alternative sign, we can decide to use it here. We have that this absolute value sign, it will cancel this alternative series time completely. So minus 1 raised to power n bracket n plus 1 over 2 is gone with the absolute value sign. Then we'll be left with the summation from n equals to 1 to infinity of 1 over 3n. So we're left with it. The absolute value have cancelled this negative sign raised to the power of n into n plus 1 over 2. So the equation becomes so easy to solve with. So we're going to test if the series converges. Now remember that it is the absolute value of the summation of an that gives us this. We go started from here and we are here now. So this, the absolute value of summation of an is actually equals to the summation from n equals to 1 to infinity of 1 over 3 raised to power n. Now let's test if this series converges. Now look at this series carefully. Now what does this series look like? To which does it belong to? With careful consideration, you observe that this is a geometric series. Remember that geometric series has the form, the summation from n equals to 1 to infinity of a over b all raised to the power of n. And these two are quite similar. Why? This expression here, which is the summation from n equals to 1 to infinity of 1 over 3 raised to power n, is the same as the summation from n equals to 1 to infinity of 1 raised to power n over 3 raised to power n. Of course, 1 over 1 raised to power n is the same thing as 1, and this is equals to the summation from n equals to 1 to infinity of 1 over 3 all raised to the power of n. So this expression here and this are quite similar. Now, according to the geometric series test, we have that given the geometric series, the summation from n equals to 1 to infinity of a over b all raised to power n, let arrow be equals to a over b. And the absolute value of arrow is less than 1, then the series converges. But when the absolute value of arrow is greater or equals to 1, then the series diverges. So this is actually the geometric series text. But the series that we're working with, the summation of 1 over 3 raised to power n from n equals to 1 to infinity, which is equals to the summation from n equals to 1 to infinity of 1 over 3 all raised to the power of n. Now, when we compare this expression with this given one, we observe that a over b is equals to 1 over 3. And so since arrow is equals to a over b, arrow will be equals to 1 over 3. So arrow is equals to 1 over 3, and 1 over 3 is equals to 0.333. And let's consider the absolute value of r, which is equals to the absolute value of 0.333. This is equals to 0.333, and it is less than 1. So the absolute value of r is less than 1, and when the absolute value of r is less than 1, the series is said to converge. So hence, the absolute value of the series of an converges. So what is our final conclusion? Since the series summation of an converges by alternative series test, and the absolute value of the series converges by geometric series test, then the series is said to converge absolutely. And that is the conclusion. Let's move over to the next example. Example 2. Consider the alternating harmonic series. The summation from n equals to 1 to infinity of minus 1 raised to the power n plus 1 all over n. And this is equals to 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. Let's keep on going. We are going to investigate whether this series is absolutely convergent or conditionally convergent. First, if you observe, this is an alternative series. Now, while dealing with an alternative series, it has this form, which is the summation from n equals to 1 to infinity of minus 1 or raised to the power n of an. So this is an alternative series, and it's quite similar with what we have over here. What we have here is the summation from n equals to 1 to infinity of minus 1 raised to the power n plus 1 all over n. And this is equals to the summation from n equals to 1 to infinity of minus 1 raised to the power n plus 1 times 1 over n. Now this expression here is quite similar with this one. Then an will be equals to 1 over n. So an, the sequence, is equals to 1 over n. Now, in an alternative series, there are two conditions for that series to converge. The first condition is that the sequence must be decreasing. That is, an should be greater than an plus 1. Now, an is equals to 1 when n is equals to 1, 1 over 2 when n is equals to 2, 1 over 3 when n is equals to 3, 1 over 4 when n is equals to 4, and it goes on. Now, 1 is greater than 1 over 2, is greater than 1 over 3, is greater than 1 over 4. Hence, it can be said that an is greater than an plus 1. So the first condition for an alternative series is satisfied. It is decreasing. Now the other condition for it to converge as an alternative series is that the limit as n tends to infinity of an must be equals to 0. Now let's check. The limit as n tends to infinity of an is 1 over n. Now this is 1 over infinity, which is 0. So the other condition is satisfied. Hence, the series converges by the alternative test. Yes, the series converge by the alternative series test because the two conditions, which is it is decreasing and also the limit of an is equals to 0. Now, for this series to converge absolutely, then the absolute value of the series must also converge. So we're going to calculate for the absolute value of the given series. Now let's solve for it. The absolute value of the given series is equals to the absolute value of the question given, which is the entire of this expression here. The summation from n is equals to 1 to infinity of minus 1 raised to the power n plus 1 all over n. Now this is equals to the absolute value of the summation from n equals to 1 to infinity of minus 1 raised to power n plus 1 times 1 over n. Now this absolute value will deal with the negative part of it. The negative part of it will cancel the absolute value. So we will be left with the summation from n equals to 1 to infinity of 1 over n. This is the harmonic series. Now in this series, to test whether it converges or diverges, we're going to use the P-series test. The P-series test. It states that if we have a series which is a summation from n equals to 1 to infinity of 1 over n raised to power p, and p is greater than 1, the series converges. But if p is less or equals to 1, the series diverges. So this is the P-series test. Now, the series we have right here is the summation as n tends to 1 to infinity of 1 over n. Now, the power of n here is 1. If we compare it with the P-series test from n equals to 1 to infinity of 1 over n raised to power p, so we have that p is equals to 1. And from the condition given in the P-series test, if p is less or equal to 1, it diverges. So hence, the series diverges by P-series test. So what will be the conclusion? In the work so far, this series actually converges by alternative series test, but the absolute value of that series diverges by P-series test. So hence, since the series summation an converges, but the absolute value of the summation of an diverges, hence the series is conditionally convergent. If you want to learn more about conditionally and absolute convergence, or you want to learn more about any of the series tests, just message me directly on WhatsApp. Meanwhile, subscribe, like and share this video. I'll see you in my next video.